Good morning, good evening. My name is Wei Yan. I'm a professor of architecture. Thanks for coming to my talk about augmented reality for digital twins, from Lego to buildings. First, I'd like to ask the audience to recall your experience about the DIY.
I'm supposed to attach a brackety thing to the side things using a bunch of these little worm guys. I have no brackety thing, I see no worm guys whatsoever, and I cannot feel my legs.
What's this?
I have no idea.
Done with the bookcase.
So that was the very first episode of Friends. Actually, instruction booklets are widely used for guiding assembly. This is Lego Arc de Triomphe. We have developed the BRexit, which is an AI instruction app for Lego assembly, by superimposing a virtual model on the physical Lego to guide assembly. Our team is interested in physical and digital twins, especially when they are registered and working together in AR. BRexit guides assembly step by step with virtual bricks. For example, the virtual bricks in the center guides step 180. A new virtual brick guides the next step. High accuracy of model alignment between physical and virtual bricks can help reduce construction errors. Because most Lego bricks are very small, high accuracy of model alignment is essential. Otherwise, mistakes will happen. For example, misplacing a brick and having to backtrack, which can be very frustrating. Step-by-step object occlusions are achieved for effective visualization. In this step, the virtual brick occludes the physical bricks behind it correctly. And in the next step, the completed physical brick occludes a new virtual brick, also correctly, helping the player understand the spatial relationship between the virtual and the physical bricks. By default, the virtual model appears in front of the hand, which does not reveal the correct spatial relation between the hand and the model. In BRexit, hand detection and occlusions are accomplished, so the virtual model can be grasped by the real hand for a realistic, immersive AR experience. Very importantly, the construction process can be augmented by information about art and architecture to enhance learning. For example, in step 137, the microfigure represents the sculpture of Napoleon crowned by the goddess of victory. The context information and image associated with the brick are displayed for the player to learn the history and art. This video demonstrates BRexit in action. Well, literature showed that AI instructions made assembly more effective. BRexit proved that highly accurate registration and realistic step-by-step occlusions enable AR instructions for tiny parts assembly. Yet there were good questions about BRexit. For example, a YouTuber asked, will BRexit take away spatial reasoning and mental rotations from children playing Lego? Our response is that we need to do research about this, but basically, BRexit is a game which can be designed to fulfill different purposes. For example, guiding assembly by reducing cognitive loads, or training spatial reasoning by increasing cognitive loads, like different game levels. Beyond instruction for assembly, we are also interested in STEM learning for spatial transformations and their mathematical representations, such as Euler angles, matrices, and quaternions, which are widely used but challenging to learn. We studied many ways of teaching spatial transformations. And this is an excellent lecture on Euler angles by Dr. Christopher Lam from Boeing Company.
Hello everyone and welcome to another video. Today I'd like to talk about Euler angles. Euler angles are three angles that were developed and introduced by the very famous mathematician Leonhard Euler in the 1700s, and we're going to see that they help play a very important role in describing the orientation of an object in space. So the first thing I need to talk about is orientation with respect to what? So we need to define a reference coordinate frame, and I think that's pretty easy to do. Why don't we take some virtual point, maybe right here. I'll call this the origin where my fist is. And in my case, north is actually pointing directly that direction. East is coming out of the page directly toward the camera, and then a right-handed coordinate system is going to make the z-axis be the down axis, which is obviously down toward the floor. Now, as I'm sure you know, you can attach another coordinate frame to, say, this aircraft. So this aircraft has a center of gravity. Let's call that the origin. Let's place that origin at the same origin as this northeast down frame. So for example, right here, something like that. What we want to do is we want to be able to describe how are these two frames quote unquote misaligned or different than one another, right? What is the orientation of the body frame with respect to this reference frame or the northeast down frame? Now, we're going to see that is exactly what Euler angles do. They help us describe these the differences in these two frames. So what we need to do is we need to jump over and start thinking about exactly what are the definition of these Euler angles, as well as develop some of the mathematics that might be necessary to operate on Euler angles and subsequent operations. So here's maybe our wing, here's the cockpit, right? So again, maybe the better way to do it is look at our prop. So we did a couple of things. First of all, we were aligned with the northeast down frame. We rotated about the z-axis through angle psi. That got us to this orientation, okay? And now what we're gonna do is we're gonna rotate about the common y-axis, which is coming out of the page, up through angle theta to get this thing pitched up slightly, okay? Great.
So to explain Euler angles, on top of the lecture video, Dr. Lam tried to draw the reference coordinate frame and the aircraft body frame over the physical aircraft. Using the physical aircraft and the virtual frames together was very effective in teaching the complex spatial transformations and math. But isn't this augmented reality? Imagine Dr. Lam had AR in his lecture. Imagine each student in the lecture holding an aircraft model, rotating it, and seeing Euler angles in hand. This idea is aligned with our recent NSF project, using AR and AI to improve teaching and learning spatial transformations, taking the advantages of AR's unique power, integrating embodied learning and visualization. This video shows our prior work and some ideas for the NSF project.
Learning geometric transformation, an AR-powered approach. This application uses ARKit to register the physical model through the AR camera. After opening the application, you are taken to this screen where you can scan your LEGO set, and a wireframe model will appear superimposed on the LEGO model. At this point, the coordinates of both the wireframe and model are zeroed out. Transformation as motion. Now you can move and rotate the LEGO model around the scene as the program tracks its location in relation to its initial position. The matrices displayed at the top of the screen detail the calculations done by the program. Transformation as mapping. This refers to the distance line and rotational arc between the image, or the LEGO model, and the pre-image, which is the wireframe model. The measure line and rotational arc, besides the notations corresponding to the distance and rotation angle, demonstrate the mapping operations of the implemented transformations of the image and the pre-image. Students can push a mapping button to display points and coordinate systems on the image and pre-image besides the lines connecting the corresponding points, demonstrating how the pre-image is mapped to the image. Transformation as function. The corresponding mathematical representation of geometric transformations are displayed through transformation matrices. The first row of matrices show the transformation matrices of the Lego model, and the second row of matrices corresponds to the wireframe model's transformations. You can apply transformations on the digital wireframe model through sliders as function parameters and track the corresponding matrix representations.
And furthermore, we want to improve architectural education using AR. In architecture, cross-section views are major design documents, but difficult for students to understand and create. For example, given the 3D view of the walls on the left, which one on the right is the correct 2D section view? And it can be much more complex than this in a real-world project. Our idea is to utilize physical buildings and their information models in AR to teach architecture and modeling. This is our MSc building on campus. This is the building information model of MSc designed by Perkins and Will. Another view of the model. 3D scanning can make building information models up to date. By superimposing beam on the physical building, AR may have broad applications in design, construction, and education. In this experiment, the AR registration is highly accurate. But more importantly, cross-section views can be studied in the building with AR visualization and embodied learning. Now, imagine Russ had AR with him. So we expect that friends assembling furniture, Dr. Lam teaching Euler Angles, and students learning architecture would all benefit from augmented reality. The benefits are being evaluated through our user studies, which are showing promising results. Thank you. Please let me know if you have any questions.
Thank you so much. It's very interesting. Any questions from the audience? Anyone?
Hi, John.
Hey, go ahead.
Hey, hi. Thanks for the talk. It's very enlightening. I really like it.
Thank you.
I have a question for you. Does your capabilities allow for dynamic modeling, or that this is like in the Euler angle type of example? What happens if the aircraft is actually flying?
Yeah, that could actually be added because it's actually can be developed using the game platform like Unity. We can add dynamics, animations into AR. Just like in the last video for showing the installation of the IKEA table, we had the animation to show the operation or installation process. So it will be great to add the dynamics into the AR,
Sure.
especially for the Euler angles. That would be very very well designed for students to learn not only mathematics but also computational algorithms, computer graphics, etc.
Sure. Yeah. Very nice.
Thank you. Yeah.
Go ahead, Amanat. I'm sorry if it's.
Thank you.
Yeah.
Very nice presentation. Thank you so much. One quick question. So in those displays that you're showing, are these doing inverse kinematic calculations? So like when things are being moved and the matrices are being updated, are they, because I'm just trying to get to it in terms of, do you encounter any singularity issues while doing the matrix calculations?
Yeah, so the way we do it is to detect the transformations of the physical model. And we do have the original like anchor point of the physical model, which could be regarded as the origin of the world coordinate system. So there is actually an invisible virtual model on top of the physical model. And there is this visible virtual model. So we actually display the relation between the two virtual models, but one of them is aligned with the physical model and it's hidden. So the students will see only the physical model in relation to the virtual model. So this is like the interplay between the physical and the virtual model to help review the transformations. And in the meantime, because we know the transformations, the rotation angles, the distance, X, Y, Z, and we can plug in them into the matrices for matrix multiplication, which is actually also used to transform the objects in the AR scene. So this matrix is displayed to help students understand their relation with the physical manipulations, but they are actually used in the computer graphics calculations.
Okay, no, that's good. I mean, because I know I wasn't sure what methods you used. I mean, I know that quaternions can help solve that problem, but if you get to 90 degrees and you're trying to get to matrix calculations, you can run into some issues at that angle.
That's right, and we also are going to look into other mathematical representations, for example, quaternions, to help resolve problems of like interpolation problems of rotations.
Mm-hmm. All right, thank you so much.
That's great, thank you.
It's great. Anyone else? Any other questions? Okay, actually, I do have one comment. You know, the one reason I'm willing to spend like $200 to buy a Lego toy for my kids is that I can get, you know, one piece, 1 week of peaceful time. Now with this app, you just ruined it. So the kids can get things done quickly. But I think it's a wonderful
that was
tool.
exactly the question asked by the YouTube user here. As we saw.
Different perspective. I saw the comment.
Yeah.
Yes.
So the thing is, we can make this game. If you want to make it harder, you can make it harder. So you can, for example, design the installation process so that the app will show 3 steps in a row, and then hide them. Then you need to complete the 3 steps altogether. Can you memorize the 3 steps and then like insert the bricks correctly in their locations and orientations? So this is up to design, how you design this.
Yes, actually, this also could be combined with art history, education,
Yes,
and some other things
right.
that Andrew's live lab, they are working on similar things, but they are focused on different,
Right,
parts.
that I understand that. Yeah, I'm aware of their work. Yeah.
That's great. Do you have any other questions? So there's the one here. Since we are already past the time, so how about you to talk offline, and we'll just take a short break, and we'll get back and get back at 10:50 with Xingyue give us a talk on digital twins for urban disaster science. Okay.
That sounds great. Yeah.
Okay, thank you.